Welcome to the lesson, Powertrain Mounting. In this lesson, we will look at the Engine Block 3D tool and the Mount Design Assistant application that can be used for mount design as well as optimization. Our goal is to demonstrate the importance of decoupling electric motor modes. With vehicle electrification gaining significant momentum, the system design approach also must change accordingly to fit the needs of the applications. The EV powertrains weigh somewhere between 100 to 150 kilograms, significantly lower than the conventional combustion powertrains. With this lighter weight, the mount location, orientations, and stiffnesses play a crucial role during the design process. Also, the electric powertrain mounts are usually stiffer than the combustion engine mounts, which reduces the static displacements and quantity, usually either 4-point or 3-point mount systems, with bush-type mounts in most cases. As with conventional powertrains, it is crucial to decouple the powertrain rigid body modes with other driveline and vehicle modes. A low dynamic stiffness value is generally desirable as the e-motors excite higher frequency vibrations. However, the modal targets for electric powertrains must be adjusted due to the absence of idle vibrations, for example. And since electric powertrains are subjected to high torque and corresponding high torque fluctuations, the mounting systems for electric powertrains are generally much stiffer. With all these points in mind, L.Nguyen's Mount Assistant tool can help design and optimize application-specific mount systems. We will specifically look at a 3-point mount system and go through the steps of decoupling the rigid body modes. Here we have a simple model of a vehicle powertrain with the mounting system. The mounting system contains 3 engine mounts with variable stiffness and damping. Let's assume that the engine, or electric motor in case of an EV, is oriented in the transverse direction. The powertrain moment of inertia values and the motor weight are listed in the table shown. These values will be used in the Mount Design Assistant tab to estimate motor mount positions for natural modes decoupling. The Mount Design Assistant is part of the 3D Engine Block tool and can be accessed from the Parameter tab. It provides a pre-visualization of the engine block and engine mounts in a 3D space, which makes the parameters setting easier by showing the positions and the orientations of the reference frames, the engine block, and the engine mounts. The crankshaft orientation, engine block mass and inertia, as well as the engine mounts properties, are displayed in the tab, Model Parameters. In the second tab, Frames Coordinates, the origin of engine reference frame as well as the position of center of gravity can be defined. And, as mentioned, the Mount Design Assistant helps the user to find the optimal mounts properties in order to decouple the rigid body modes, where mounts properties, positions, orientations, and stiffnesses can be optimized. The modal kinetic energy distribution matrix is used to check whether the rigid body modes of the engine block e-motor are decoupled. The decoupled modes are highlighted in green, and partially decoupled modes are highlighted in yellow and orange. The general idea of the optimization process is to decouple the engine block rigid body modes, X, Y, Z, roll, pitch, and yaw. Decoupling the engine block rigid body modes means to separate them in order to control them and tune their natural frequencies. In other words, tuning a stiffness will impact the value of the corresponding natural frequency, keeping the other frequencies unchanged. The optimization routine can be used to optimize mount stiffnesses by setting additional constraints and targets such as bounce mode and roll frequency targets. In this iteration, we set a roll mode frequency target of 10 Hz as well as adjusted the mount location. After optimization, we observe that all the model are perfectly decoupled and modal kinetic energy of each eigenfrequency lines up with 1 degree of freedom. Achieving a diagonal values of more than 90% represents a full decoupling of rigid body modes, which means that the modal kinetic energy is concentrated in only one mode. The mount properties displayed in this section are not directly linked with the model parameters. Using the Reset and Apply buttons, the mount properties can be updated to reflect on the model parameters.